Audio Jungle. Audio Jungle.
Hello everyone, myself Narendra Singh Maurya and hope you all are doing well. So guys, today we'll solve jet propulsion problem GATE 2021 and this is the problem number 5. The combustion process in turboshaft engine during ideal operation is, okay. So the combustion process, right? So option here, it is isentropic. What is the isentropic? It is reversible, adiabatic. Isobaric means at constant pressure process, okay. Isochoric means at constant volume process, means at constant pressure. If a combustion process is what conducting, so it is called isochoric, and if it is at constant temperature, suppose having combustion process at constant temperature, then it will be called as a isothermal. So you know all the engines, aircraft engine will follow the Brayton cycle, right? So if you check in this case what is the Brayton cycle, so you may understand this easily. We'll have a TS plot, temperature versus entropy. We know this is the Brayton cycle, which is nothing but two constant pressure line and two reversible adiabatic. So this reversible adiabatic is what at uh, for the ideal case it is like compression is what always at uh, like a isentropic process. So here 1 to 2, this is the compression, okay, and 2 to 3, this is what heat addition, which is also called a combustion, okay, and here we have a heat rejection, and 3 to 4 again there is the expansion. This is the general cycle I'm explaining here, Brayton cycle, okay. So what happens basically, always heat, whenever the combustion process will be there in case of the engine, turbo engine, so it is at constant, because 2 to 3 is what is 2 to 3? 2 to 3 is the constant pressure line, okay. 2 to 3 is nothing but constant pressure line, all right. So at constant pressure line, or you can say at constant pressure you are adding heat, okay, 2 to 3. So it means combustion process is what in combustion what will happen, we are adding heat, all right, we are burning fuel with the air, that will be called as a combustion, all right. So it means we are adding heat. So at constant pressure heat will be added, hence the combustion process in turbosoft engine during ideal operation will be at constant pressure, and that is nothing but option B, which is called isobaric. Hope you understood this, all right. Anyway, next, so this is problem number 6. How does the specific thrust of turbojet engine change for a given flight speed with increase in flight altitude? So they have given what they have given. Suppose any jet engine we have, right? We have jet engine. This is the aircraft, and wing. Similarly, this is the horizontal tail. Okay, and suppose that engine, which is nothing but turbojet engine, it is on the main wing. Okay, so this is the engine. All right, just a general idea. So in this case, this aircraft is what flying. This aircraft is what flying at some altitude, and it is fixed. Okay, they have given speed with increase uh, in flight altitude. So sometimes it is flying with just say aircraft is what here at some particular time. Okay, h1 altitude, and then it is going for next altitude from the surface H2. H2 is greater than H1. Yes or no? So altitude only we are changing for a given flight speed. Okay, so speed is what constant. Speed we are not going to change. For both cases, speed is what constant. So speed is what constant. They have clearly mentioned. Okay, what we are changing here? We are changing the altitude. Huh? How does the specific thrust of turbojet engine change for a given flight speed with increase in flight altitude? All right. Anyway, so now if we'll solve this, so it's a simple. Uh, we'll write the thrust for the turbojet engine. Okay. So we know. So thrust is basically very basic momentum thrust. Okay, and pressure thrust. All right. Suppose here. Okay. Now this is the engine. All right. And for this engine we have a air, which is nothing but m dot a, that is air, and we have fuel addition in combustion chamber. Okay, all right, and then we'll have exit. This is the gas, so that exit will be m dot a plus m dot f. Okay, what is the exit velocity? Ve. What is the inlet velocity here? I must write, it is nothing but v infinity. Okay, to just say like here that exit pressure and that here inlet stream free stream pressure is nothing but v infinite. All right, and what is the exit pressure? It is nothing but p. If I will write thrust formula, so what will get? Change in momentum m dot a m dot f into ve minus m dot a into, this is the momentum thrust, plus pe minus p infinity into exit area. Pressure into area will be the force, means that is thrust. So here we have area A. All right. Now we need to check what will happen when altitude will change. Hmm? So you all know altitude change means three effect. Thermodynamics effect, that is pressure will change. Okay, temperature will change, and density will change. This is the scenario here related to the question. Now we check. They are saying what will happen to the specific thrust, okay, of a turbojet engine when change for a given flight speed with increase in flight altitude. Means if flight altitude is what changing, then what will be the specific thrust? Increases, decreases, remains constant, first increases and then decreases. So this is the question. All right. Now, so thrust formula you have written here. What is the specific thrust? I will say it is Fs, which is nothing but thrust divided by mass flow rate of the air. So if you write this, then what you will get? 1 plus mf by m dot a into ve minus v infinity plus ae by m dot a in bracket pe minus p infinity. Yes or no? So let me correct, this is AE. All right. So be specific now. This is because we have to write the specific thrust, so we need to write the formula. We know what is the m dot f divided by m dot a. This is fuel air ratio, hmm, fuel air ratio, which is also noted by small f. So what will be the specific thrust now? Fs, thrust divided by mass flow rate of the air, is equal to 1 plus f ve minus v infinity plus ae divided by mass flow rate of the air in bracket ee p infinity. Okay. Now check. So we'll check the effect and in this case I must say this is the momentum thrust and this is what pressure thrust. All right. Now check altitude increasing or decreasing. Based on that we have to answer. Increase in altitude. Okay. Increase in altitude. When altitudes increases, okay, density decreases, pressure decreases, and temperature. Okay, temperature decreases in troposphere. So for troposphere I'm writing here. Okay, in stratosphere temperature will be constant, rest density and pressure will be decreasing. Anyway, so once altitude increases, density decreases, pressure decreases, temperature decreases. So what will happen? Because speed is what constant, so this quantity is, which is the free stream, speed of the free stream or speed of the aircraft, it is a constant because for given aircraft speed they are saying, so v infinity is what constant. All right. Now we'll talk about the uh, rest quantity. What are the rest quantity? Check that first p infinity. If p, check the p infinity, which is the atmospheric pressure, obviously ambient pressure or atmospheric pressure, all right, or surrounding pressure. P infinity will be decreasing. If P infinity decreasing, then this total difference between pe minus P infinity will be increasing. Okay, so I must write here when altitude increases, pressure decreases. So P infinity, I'm talking about P infinity, not vp pe. P infinity will be decreasing. This P infinity will be decreasing, then overall effect means overall the value of the bracket will be increasing. Overall value of the bracket will be increasing because it is the difference. So if this bracket value will be increasing, so automatically specific thrust will be increasing. All right. I hope you all understand this. Yes or no? Very generic formula from the nozzle. This is suppose nozzle because obviously whatever the exhaust you may have in jet engine, thrust you are getting from the nozzle. So for the nozzle, if the this is the V exit velocity, so temperature will be TE, or total temperature I will write T naught E. Yes or no? And we have surrounding temperature which is T infinity. What is the VE? What is the VE value? That VE is nothing but it's a simple formula, you know that 2 Cp T naught E minus T infinity in bracket. For the nozzle, I'm not going for this derivation because it will take time. It's a MCQ. I just wanted to explain the fundamental of it so that you can answer for other questions. Similar question will be asked in future also, so you can answer. For that reason, I'm taking so much time and I'm explaining. Otherwise, we can finish this question in within second. All right. So check VE. This is the formula, exit velocity formula for the nozzle. Okay. So here we have a T infinity. Check T infinity. Temperature is also decreasing here when altitude is increasing. If temperature is decreasing, so again I must say uh, this value, okay, I must say this T infinity value, this is what decreasing. So this T infinity is decreasing, then what will happen to V infinity, VE exit velocity? Obviously it will be increasing. Why? Because T infinity is decreasing, then this bracket value, whole bracket value, whole bracket value will be increasing. Yes or no? Whole bracket value will be increasing. Check this whole bracket, because difference will be decreasing, because T naught is the total temperature which is constant. So T infinity, because altitude increasing, so temperature will be decreasing, hence this bracket value will be increasing, and you are finally getting V is also increasing. Now hope you got the answer. What is the answer finally? Because VE is increasing. So if VE is increasing because altitude is increasing, okay, and this whole bracket also increasing, so overall effect of the specific thrust will be increasing. No chance of decrement of a specific thrust. What is the correct answer? Increases monotonically, decreases, remains constant, thrust increases, then decreases, so all are wrong. What is the correct answer? Option A. So what is the answer? Answer is option A. Hope you all understand this. Yes or no? Here also, what was the answer? Answer was option B. Answer is A. All right. Increases. Anyway, we'll go for next question. This is the next question. Check. How does the propulsion or propulsive efficiency of turbofan engine operating at a given Mach number and given altitude? So here they have given one thing, condition again here it is given that turbofan is what operating at a given Mach number. So Mach number become constant, okay, and altitude h is also constant. It is said like it is given means it is constant, it is not going to change. Now they are saying change with increase in compression pressure ratio. If compression pressure ratio will change, then what will be the propulsive efficiency? This is the question. All right, this is the question. So in this case, we'll have the propulsive efficiency formula, general formula for the turbofan. So yes, wait. So you can say propulsion efficiency or propulsive efficiency for turbofan. We know generally turbofan, we can draw the simple diagram. Suppose this is what fan, okay, and this fan is what connected to the shaft, and then again we have a compressor, okay, we have a combustion chamber here, then again we'll have a high pressure turbine, okay, and we have low pressure turbine also. All right. So what will happen? Suppose this is the fan. So this is the one part, I must say, okay. You say compressor, we just increase this. This is the fan. You all know the concept of the fan and all, okay. So check. This is the outer cowling. Yes or no? With this general idea I am giving, so you can understand easily. Now we'll have flow of air. This is what m dot a. What this fan will do? This fan will divide the stream. What stream? Few parts of the air will go in this path, and few parts of the air obviously will go in this path, and that few parts of this air will also go through this core part. This is the hot air. I should not draw with blue color, but okay. It is a hot air. So I must draw by red. So this is the hot air. In combustion chamber, it will get heated because we are burning fuel and all. So basically, this amount is nothing but m dot h or hot, and this is nothing but m dot c. So what is the m dot a, which is nothing but m dot c plus m dot h. Okay, hot and cold air you understood, and whatever the velocity here you may get, this is the v exit cold, and here obviously this is also v exit cold. Why I am writing? Because I want to write the formula, so you should know all the things. V hot. Hope you understood. Now the formula is propulsion efficiency. Okay, just like for the jet engine also, you know the formula turbojet. Okay, we have a turbofan formula. So we'll write 2 into V infinity. This is the free stream air, so this is V infinity to V infinity. All right, in bracket it is V hot plus beta. I will tell you what is the beta. V cooled minus 1 plus beta V infinity. All right, divide by VE hot square beta cold 1 plus beta V infinity square. This is the formula. All right, now they are saying, now this is the propulsion, and hope you understood what is the V hot, what is the VE cold. Yes, beta I just wanted to tell. Beta is nothing but bypass ratio. What is that? Bypass ratio, which is nothing but m dot cold divided by m dot hot. Means cold air and hot air, it is divided by fan. Yes or no? So how it is divided in that way? You can use the it is a performance parameter, bypass ratio beta, m dot c by m dot h. How much of air going through the cold jet? This is called cold nozzle. This is the cold nozzle part, because air is passing through this, and here this is the hot. So you got the idea about turbofan. Yes or no? This is what fan. Anyway, now we'll go for the, hope you understood this whole things. Now we'll go for the question. They are saying change in with increase in compressor pressure ratio. So they are saying Mach number is what constant. See, for a given Mach number is constant. Here I have written already. Altitude is constant, so no pressure and temperature is what changing. Okay. Now they are asking propulsive efficiency. This part they are asking, and they are saying we are changing the compressor pressure ratio. You tell me, if you are changing the compressor pressure ratio, so any effect you will talk in cold uh, uh, that nozzle, because you are changing the quantity in hot nozzle. Okay, in core path. This is called core also. This is the core channel. Okay, so compressor pressure ratio you are increasing here. Okay, so another also one thing you can say, like effect of the velocity in cold air, again it is not going to change because of the compressor. Whatever the cold air velocity, that will be constant. It is not going to change. Only the effect you are going to get in the hot, because compressor pressure ratio we are changing. Yes or no? So if you change the compressor pressure ratio, so compressor pressure ratio if you change, okay, one more thing I will write, compressor pressure ratio. Okay, so if you change this compressor pressure ratio, so two effect you may get, TIT, which is called turbine inlet temperature, and thrust. In two places you will get the difference. Okay, in thrust and turbine inlet temperature, if you increase the compressor pressure ratio. All right. Now, so if you started increasing the compressor pressure ratio, okay, so what will happen? Check. Now, first of all, TIT means turbine inlet temperature will be increasing. Okay, turbine inlet temperature will be increasing, and if turbine inlet temperature will be increasing, then velocity, exit velocity will be increasing. Yes or no? If you are increasing compressor pressure ratio, so turbine inlet temperature will be increasing, and that exit velocity will be increasing. Okay. At the same time, if you talk about the thrust, okay, if you talk about the thrust, so what will happen to the thrust? Obviously, thrust will also be increasing. All right. Here, that cold velocity, because it is in cold channel, so it is not going to change. So you can say uh, whatever the change in compressor pressure ratio, that will not affect the cold velocity. Okay, so what will happen if you increase the compressor ratio, pressure ratio? So it means you are not going to burn the more amount of fuel, because TIT and thrust you can increase by burning the fuel. Okay, but if compressor pressure ratio if you are increasing, it means that even the less amount of the fuel also, if you are burning, then you will get more TIT, turbine inlet temperature, and thrust. All right. So what will affect to the propulsion efficiency? In that case, propulsion efficiency check. I will write another formula also, so you may understand 2 alpha divided by 1 plus alpha. Like what will happen to this case? 2, this is nothing but Ci by Cj, that is exit velocity. And this is again 1 plus alpha, which is nothing but Ci by Cj. Okay. So now if you check the propulsion efficiency, so first, if you increase the compressor pressure ratio, so initially that exit velocity will be decreasing. Okay. Then what will happen? Then obviously, if exit velocity will be decreasing, then your propulsion efficiency will be decreasing. But once you start compression pressure ratio more and more, okay, so because of the increment in turbine inlet temperature, that exit velocity will increase rapidly. Once exit velocity will be increasing in hot, I am saying in hot nozzle, so that propulsion efficiency will start increasing. Yes or no? So what will be the correct answer? Because once you start compression pressure ratio, so first propulsion efficiency will be decreasing. Okay, then it will start increasing. That's the answer. You can relate this velocity, so you may get the idea. Okay, so what is the option? Because if you start that compression pressure ratio immediately, so automatically that exit velocity you will not get more. It will take time. Okay, so first it will decrease and then it will increase. All right, so what is the correct answer? Option D is the correct answer here. Okay. All right. Now, okay, in like another way how to relate this, also you can see like even though cold velocity, because if you are burning less amount of fuel, it means your thermal efficiency will be high. And what about propulsive efficiency? Efficiency will be related to a propulsive power. Okay, and in that propulsive power, first if you talk about the exit velocity, so once compression ratio will be increasing, then turbine inlet temperature will be increasing, and then you will get more velocity. So initially it will decrease, and then it will start increasing. Okay. So what is the correct answer here? Option D, because remains constant not possible because compressor pressure ratio are increasing. Increases monotonically, that is also not correct, because first that velocity will be decreasing. So obviously you will get less propulsive efficiency, and once enough turbine inlet temperature will get, then velocity of the jet will be increasing. So in that case you will get more propulsive efficiency. Yes or no? So this is the third is decreases monotonically. No, first decreases and then increases. That is the correct answer. All right. Now, this is the next question, question number 43. All right. So here, this question is, an aircraft with turbojet engine is flying 270 meter per second. Okay. This is turbojet engine. So given quantity, I must write first. Flying with 270, so I can write VV infinity or aircraft speed, which is nothing but 270 meter per second. All right. The enthalpy of the incoming air at the intake is, okay, so enthalpy of air at intake is, they have given. So I can say intake, I will say atmospheric, so HA is nothing but 260 kilojoule per kg they have given. All right. And the enthalpy of exhaust gases at the nozzle exit, so enthalpy of the exhaust gases, how much? 912 kilojoule per kg. Okay. The ratio of mass flow rates of fuel and air, so ratio of mass flow rate of fuel and air, m dot f, which is also called fuel to air ratio. Okay, how much it is? 0.019. The chemical energy of the fuel is, so that is called the heating value, HV, how much? 44.5 megajoule per kg. And the combustion process is ideal. All right, means what is the mean of it? It means combustion chamber efficiency is 100%. Magnitude, if you write, then it is unit. Na? Total loss of heat from the engine to the ambient is 25 kilojoule per kg of air. Okay, so this value I will write here. So first I will general turbojet engine, which is following the Brayton cycle. Okay, so I will draw this Brayton cycle, TS, two pressure line. This is two pressure line, compression and expansion. Okay, this is the compression. Okay, I must say air is what entering A. Okay, this is what A, or you can say station 1, and this is station 2. So inside the engine you write total quantity station 3, and this is what station 4, or you just say exit is what, don't write a total quantity, exit is always static, so write this. And you can say exit is nothing but E also you can write. Hope you understood this. All right, now we'll write this. See, so whatever the loss they are seeing, that loss is nothing but they are saying, if you check, this loss is total loss of heat from engine to the ambient is 25 kilojoule per kg of air. So total loss they are talking, so total loss of the uh, heat from the engine. So engine means total loss that engine, if they are saying, so you have to relate that we have this is the turbine. Okay, a turbine inlet temperature. So now in this diagram you can understand that total loss of the enthalpy, which is nothing but H naught 3. Okay, H naught 3 minus whatever the total loss at the exit, exit will be ambient, so it is nothing but H naught E, and this loss they have given how much? it is given 25 kilojoule per kg of air. So 25 kilojoule per kg. This is the value. All right. Now, what we'll do here, this is the one ratio we got. Now check the total loss, the velocity of the exhaust jet is. So velocity of the exhaust jet they are asking. So means VE. And one more thing we know, H naught, velocity of the exhaust means VE they are asking. What is the H naught E at the exit? Total enthalpy will be static enthalpy at the exit. I must write exit. Okay. Exit plus exit velocity by 2. This is the VE square by 2 is the velocity equivalent to the enthalpy. So this will be the value. So what is our job? Our job is from the given data. Okay. From the given data, if anyhow would able to calculate H naught E and H naught 3. Okay. From H naught 3 we can get H naught E, and then after H naught E we can HE, because enthalpy at the exit they have given HE, this value they have given, velocity they have given at the inlet, they have given. Okay. So we can calculate enthalpy at the exit. Now in this problem, after reading all this data, you can check fuel air ratio they have given, heat value they have given, combustion chamber efficiency they have said ideal, hence it is you can say 1 or unit or 100%. All right. So we can write energy equation. Okay. So I must write this VE. What will be the VE in this case? Because I need to calculate VE, so directly I will write this. We know this total enthalpy is equal to static enthalpy plus enthalpy equivalent to velocity. So what will be the velocity here? VE. Velocity will be H naught E minus HE into 2 root. So now this is given and this is unknown. So this unknown value I have to calculate first. Anyhow, for this what I will do, I will go to this relation, that loss they have given. This is the loss, total loss. So anyhow I need to calculate H naught 3. So H naught 3 is the temperature at the exit of combustion chamber. This will be the combustion chamber. Yes or no? So because 2 to 3 is the combustion chamber, so I will redraw the combustion chamber here. This is a combustion chamber, station 2, station 3. So energy equation I will write energy, okay, equation across combustion chamber. Okay. So what is the energy equation? Check. Air is what entering here. Okay. What is the air? M dot A. Yes or no? And fuel M dot F. Then exit will be gas. Okay. Now we'll write the energy equation across the combustion chamber. So this will be, check, M dot A H naught A plus M dot F eta Cc into heat value. This is the, this is very generic combustion chamber energy equation across the combustion chamber. Sorry, M dot A, sorry, M dot A plus M dot F H naught 3. Hope you understood why I am writing this equation, because I want to calculate H naught 3. I need that value. So how you can get? You have to apply energy equation balance across the combustion chamber. Total heat input or total energy input is equal to total energy output. That is the energy conservation, heat balanced, energy balanced. All right. We don't have H naught A. We have to calculate. What is the H naught A? H naught is the total enthalpy, and because intake I'm writing H naught A here, no? But this is what H naught 2. So what is the 2 point station 2? This is the station 2. This is what? This is what intake. But about intake, across the intake, total enthalpy must be constant because we are not adding any heat in intake. So H naught A is equal to H naught 2. So whatever the value of H naught A, that will be H naught 2. Hope you understood. So better I will write this. I will write here H naught 2. So that should not any confusion. And this H naught 2, because across combustion chamber we have written here 2 and 3. So this is H naught 2. What is the H naught 2? H naught 2 is nothing but H naught A. And what is the H naught A? That is the total enthalpy at the inlet. So static enthalpy at the inlet, which is HA plus velocity of the aircraft by 2. See why I am writing this? Because I need to calculate H naught 2, which is nothing but H naught A. And HA they have given to us. How much? Check. HA they have given 260 kilojoule per kg and velocity 270. So I must write this value 260 kilojoule plus 270 square by, yes or no? This value we have to calculate. How much will get this? I'll write first 270 square by 2 plus 260 10 power 3 divided by 10 power 3. How much? 296. This is 296.45 kilojoule per kg. All right. Now we'll this is just say equation number A. Okay. We'll write putting H naught 2, which is 296.45 kilojoule per kg in equation A. What is the equation A? Check. M dot A. So M dot A into H naught is 296.45. Okay, 10 to power 3 better I will write, plus M dot F. Eta Cc is given 100%, so 1. And heat value I think they have given. How much they have given heat value? Heat value is 44.5 megajoule. All right, it is nothing but 44.5 megajoule, hence 10 to power 6 is equal to M dot A plus M dot F into H naught 3. Now this value you can write 296.45 10 to power 3 plus divide by M dot A throughout the equation. So M dot F by M dot A, okay, into 1 into 44.5 into 10 to power 6 is equal to M dot A plus M dot F into H naught 3. We know that what is the M dot F? Fuel air ratio. This is fuel to air ratio, which is nothing but small f. And check this value. I think they have given how much? They have given 0.019 fuel to air ratio. 0.0119. All right. So we'll write all the value and try to calculate the 296.45 10 power 3 plus 0.019 144.5 10 to the power 6 1 plus 0.019 H naught 3. So let me calculate this value. H naught 3, how much it is? Wait, let me calculate this. 10 to the power 3 plus 0.019 into 44.5 10 to the power 6, okay, divided by divided by 1.0019. Wait, 1.019 divide by 10 to the power 6. So into 10 to the power 3. Okay, this is 1120.65 kilojoule per kg. This is the value of H naught 3. All right, we know H naught 3 minus H naught E is equal to loss of heat, which is given 25 into 10 to the power 3. Check previous equation. See here, this value. Yes or no? Then we'll calculate H naught E. So we'll minus this value minus 25. How much? 1095.65 kilojoule per kg. All right. Now we know this H naught E is equal to He plus V square by 2. What is the VE? I told you it is 2 H naught E minus He. So H naught E minus, what is the He? They have given H naught is nothing but 1095.65 minus I will write He. How much it is given? He is C 912. Here this is given 912 kilojoule per kg. So we'll write this value 912 into all value are kilojoule. So we'll write 10 to the power 3. Let me calculate this. How much? So 912, okay, into 2, okay, into 10 to the power 3. We'll take root of it. It is approximate 606.06 meter per second. This is the answer. Yes or no? So we'll keep here. This value is what? 606 point, round up to decimal. So 0.065 it is given. This is the answer, 606. I hope you all understand this. All right. This is the correct answer. Now we'll go for the next question. I hope you all understand. Any doubt for any steps, for any calculation or any formula you are not able to understand, write comment box. Okay. Write a comment in comment box always. Okay. Now we'll go for next problem here. This is the next problem, problem number 45. All right. They have given a twin spool turbofan engine. Okay. Is operated at sea level pressure. They have given sea level temperature. The engine has separate cold and hot nozzles during the thrust test at sea level. So thrust sea level means first of all that aircraft is, because we are talking about the engine only, so aircraft speed will be 0 because it is the speed will be 0, because it is the static thrust test. No, see here it is given a static thrust test. Yes or no? All right. The overall mass flow rate of air through the engine and the cold exhaust temperature are measured. Okay, so this overall mass flow rate they have given, and temperature at the exhaust they have given for the cold. For the cold they are talking respectively. Parameters for engines, this is the fan pressure ratio, here it is given overall pressure ratio, bypass ratio, turbine TIT, turbine inlet temperature. CP value they have given to us 1.005 kilojoule per kg Kelvin. The ratio of specific heat means gamma they have given for air. The assuming ideal fan and ideal expansion in the nozzle at sea level, static thrust from cold nozzle. So you know that total thrust you may have, okay, due to cold and hot nozzle. Okay, if I say, okay, this is what turbofan. So this turbofan you can see easily, this is the total mass of the air which is already given. How much it is given? They have given 100 kg per second. So this value they have given 100 kg per second, m dot a. All right, obviously this is the fan, and this fan through this is the fan nozzle, or you can say this is the cold nozzle. This is called cold nozzle, and this is called core nozzle or hot nozzle. Core or hot nozzle. So whatever the thrust you may get here, it is due to hot nozzle, and whatever the thrust here you will get both side, you will get, this is due to cold nozzle. All right. So they are not talking about hot nozzle, they are asking about cold nozzle. They are not considering anything for the hot nozzle, or uh, like what is the thrust in core nozzle, okay, what is the velocity in core nozzle, nothing they are asking. They are interested in cold nozzle only. All right. So we'll proceed this problem. Check simple data they have given for the cold nozzle. First they have given number one, m dot. First they have given how much? 100 kg per second of air. Okay, others they have given bypass ratio, because I'm interested the thrust. So first bypass ratio, which is nothing but m dot cold divided by m dot, this is the bypass ratio. Okay, how much it is given? It is given bypass ratio 3. They have given 3. You remember m dot a is equal to m dot c. C means cold plus m dot h means hot. Okay, so from here, because you know total thrust, it is thrust due to cold nozzle plus thrust due to hot nozzle. Okay, what about the pressure thrust? We'll see here. Anything they have given for the pressure thrust? They have given ideal expansion in the nozzle. If ideal expansion in the nozzle, then exit pressure will be ambient pressure. PE is equal to PA. PE is equal to PA means exit pressure from the cold nozzle and exit pressure from the hot nozzle will be equal to atmospheric pressure. So it means what? Pressure thrust will be 0. We'll not talk about pressure thrust also, because they have said ideal expansion. So only momentum thrust will have, but in that also they are not talking about hot nozzle. So I can say this is 0, not exactly 0, but yes, because we are not interested. Now our interest is what? Here, this value we have to calculate. So what will be the formula for the cold nozzle thrust? Only momentum thrust we have to write. So we need to write m dot c, which is the cold mass flow rate into exit velocity of the cold nozzle. This hot nozzle will not talk. So our thrust will be now cold due to cold nozzle. Okay. which is nothing but m dot c into V exit in cold nozzle. So now we need to calculate m dot c. We have relation. What is the relation we have? M dot is equal to m dot c, m dot h, which is 100, and we have another relation beta, which is given 3, that is also m dot c divided by m dot h. Equation number 1, equation number 2. So from equation 1 we can write, what we can write, m dot c. What we can write m dot c? M dot c will be 3 m dot h plus m dot h, which is nothing but 100, or m dot hot nozzle mass flow rate will be 100 divided by 4, which is nothing but 25 kilojoule per kg. Yes or no? So what will be the m dot c now? M dot c will be 100 minus 25, which is nothing but 75. It's not kilojoule, it's a kg per second, right? Sorry, kg per second. 100 kg per second. So it is kg per second, sorry. Okay. So this is what? Kg per second. All right. Now we got 75 kg per second, which is nothing but m dot c. All right. Now, what value we'll calculate? We need to calculate V exit. Then we'll get the cold thrust. V exit to the cold nozzle we need to calculate. Okay. Anything for the exit of the cold nozzle they have given? Check. The engine at the cold exhaust temperature they have given. Okay. The mass flow rate and temperature. So this is what TE. Only this exit temperature they have given. Okay. Fan pressure ratio also related to cold nozzle. So TE they have given to us. So we know for the nozzle, okay, what is the velocity? Exit velocity. This is very generic from the nozzle. What is the exit velocity? You know, which is nothing but you can write 2 Cp T naught E minus TE. This is the exit velocity. Previous problem also I had used this formula. This is the, once you apply equation, suppose this is the nozzle, okay, and we have a flow here, exit, okay. So exit temperature is TE and total temperature is T naught E. Then if you want to calculate what is the velocity, okay, so VE will be 2 Cp T naught E minus T. This is the formula, very generic formula, you all know. This is what nozzle. Yes or no? So T naught E you need to calculate. TE is given. What is the TE they have given to us? TE they have given to us, which is nothing but for the cold nozzle they have given how much? 288 Kelvin. We can calculate T naught E. That fan pressure ratio they have given. So we'll go. What is the T naught E by TE? That is the fan pressure ratio, FPR. Okay. It is nothing but gamma minus 1 by gamma. All right. That is the gamma minus 1 by gamma, because it will be fan pressure ratio, and here this fan pressure ratio is what? You can say P naught E by PE, or you can also say P naught A by PA. All right. And P naught A by PA you can calculate. That you may get directly, otherwise you can use the fan pressure ratio, that will also, otherwise P naught A also you can calculate, because velocity at the inlet they have given, temperature they have given, use Mach number, you calculate P naught A, because process is ideal only, isentropic. Directly I am using this. Okay. So this value they have given to us. So what will be T naught E? T naught E will be TE into fan pressure ratio. What is the fan pressure ratio? Let me check. It is 1.6. To whole power, gamma is 1.4 they have given. Okay, you calculate this. What is the one? Wait, 1.4 minus 1 divided by 1.4. Okay, 1.6 to whole power. To whole power. Okay. So this T naught E will be at 1.6 whole power 0.4 divided by 1.4. 1.143 into TE. How much? 288. So it is nothing but 329.39. All right, Kelvin. Okay. Now you can calculate V exit. How much? 2 CP. Okay. Use this value. So exit velocity of the hole. Okay. So check how much you may get this. This is nothing but T naught E minus 288. All right. Into 2 into CP is 1005. Take root of it. It is somewhat 288.43 meter per second. What will be the thrust due to cold nozzle? It is nothing but m dot c into V cold. What is m dot c? It is 75 kilojoule per second, kilogram per second into V cooled is nothing but 288 point. Let me calculate this. How much? 75. It is nothing but 21632.92 Newton or 21.632 kilonewton. Okay, check, this was the fill in the blank. The kilonewton they have mentioned already, so you just write only 21.63. That's all. That's all. This is the answer. All right, hope you understood this. Okay, this is the solution for your question. This is the thrust due to cold nozzle only. We are not talking about the hot nozzle thrust. Okay. All right. This is the another problem. This was problem number 48. No? So we'll go for the solution for this problem again. Now check. What given data they have given? The airflow rate through the gas generator. What is the gas generator? Gas generator, it is the combination of compressor, okay, combustion chamber, and turbine. Okay, we have turbo prop engine, and for the gas generator they have given airflow rate through the gas generator. So m dot a they have given how much? It is 100 kg per second. Stagnation temperature at inlet and exit of combustor. Okay, so I will draw the, see, this is what gas generator. Okay. Compressor, combustion chamber, and turbine. This is nothing but gas generator. All right. Now they have said we are talking about only combustion chamber. CC, combustion chamber. Clearly, they have. I will mention the points. One, okay, two, three, four. So our combustion chamber is point 0.2 and point 0.3. Inside engine, we'll talk about total quantity, not 2, not 3. All right. They have given value for the check stagnation temperature at inlet of the combustor is 600 and exit is 1200. So they have given this is 600 Kelvin and 1200 Kelvin. All right. This value they have given. Means we can say T02 they have given 600 Kelvin. T03 they have given 1200 Kelvin. All right. Now burner efficiency 90% they have given. So what will happen to this? They are asking, they are saying burner efficiency 90% and the heating value of the fuel is 40 megajoule per kg. The specific heat at constant pressure for air is given and for gases. Both value they have given. For gas and for air, both CP value they have given. The flow rate of fuel being used. So what they are asking, m dot f they are asking. No? Flow rate of fuel. All right, m dot f. So basically all the quantity they have given, they are talking about the fuel rate, heat value, and also what you understand. It's simple. We have to check. This is the basically airflow. Here this airflow is nothing but m dot a. Then we are adding heat for fuel. So this is the fuel m dot f. Okay, and then exit will be, what will be the exit? Exit will be the combustor products m dot a plus m dot f. Yes or no? We'll do one thing. We'll write energy equation across burner or combustion chamber. Burner or combustion chamber. What is the energy equation? Total heat input is equal to total heat input is equal to total heat rejection. Okay. What is the total heat input? M dot A Cp, because it is air, into what is the inlet of the combustor or inlet of the burner? It is not 2. So Cp T02, fuel you are adding, so mass flow rate of fuel into burner efficiency or combustion chamber efficiency into heat value. You know this energy equation, you are much more familiar now. Exit is m dot a plus m dot f. Okay, into Cp of gas you have to write into what is the exit of burner? It is not 3, T03. All right, we need to calculate m dot f. So what we'll do, I will take one side this value. So it is m dot f is the fuel flow rate, m dot a Cp of air T02. Okay, then I will take this m dot right side m dot a part also. So m dot a Cp of gas T03 is equal to, I can write m dot f Cp of gas T03 minus, I can take this m dot f this side also, m dot f eta Cc into heat value. Yes or no? So what will be the m dot f? M dot f will be m dot a, okay, into, we can write Cp air T02 minus, okay, Cp gas T03 divide by, what is the mf? Take common, so it will be Cp gas T03 minus eta Cc into T12. We'll write all the data. We'll write all the data, so we'll get m dot f. What is the m dot a? We know that m dot a they have given for this problem. M dot a, check. M dot a is 100, no? 100 kilojoule kilogram per second. So we'll write this value 100 in bracket. What is the value of Cp of air? Once I need to write all the value. Cp of air 100,000 and Cp of gas 1200. 1200. So this value is nothing but 1000, okay, into T02, you know, it is 600 minus Cp of gas 1200 into T03 also 1200 divide by Cp of gas 1200 into 1200 T03 minus eta Cc. What is the eta Cc? That is the burner efficiency, combustion chamber efficiency or burner efficiency 90%. Here it is given. Check 90%. So minus 90% means 0.9. And what is the heat value here? It is given. It is given how much? Check 40 megajoule. 40 megajoule. We'll write megajoule. Yes or no? Megajoule per kg. All right. Now fine. So I will write this 10 to power 6. No, better. Joule per kg 10 to power. So we'll calculate m dot f. Wait. So I will write in one bracket. I will write 1000 into 600 minus 1200 into 1200 bracket close divided by another bracket 1200 into 1200 minus 0.9 into 40 10 to power 6 40 10 to power into 100. It is 2.43 kilogram per. This is the answer, 2.43. All right. So this is 2.43 kg per second unit is given. So hope you all understand. For any problem, any doubt, if you may get, then you write comment on comment box. Thank you all. Thank you so much.